Hello everyone, and welcome to the Unit 3 review for Algebra 1B. In this unit we started talking about quadratics, and you'll see that that's going to be represented as graphs such as the one you see here, as equations, as charts, and it also has a lot of practical purposes. You should be able to, by the end of this unit, use the Pythagorean theorem, use the distance and midpoint formulas, do transformations of graphs, recognize them, do them yourself, solve quadratic inequalities, graph quadratic functions, solve quadratic equations by the square root method, completing the square and the quadratic formula, compare functions, look at composition of functions, solve application problems with quadratics. So let's get started. Remember, the Pythagorean theorem is probably something you learned earlier, but we're going to review it here and use it in a lot of purposes. The basic theorem says that a squared plus b squared equals c squared, and it is related to right triangles. So over here you see a right triangle, and the two legs, the ones that come together at the right angle, are called A and B. The hypotenuse is the one called C, and that's really all you need to remember to be able to use this theorem. So if you have two sides, you will always be able to find the other one using the Pythagorean theorem. A sample question you might see on your test is determine if side lengths can make a right triangle. Do the lengths make this equation true? So for instance, if you had a leg that was 3, a leg that was 4, and a leg that was 5, could these sides be part of a right triangle? Well, if they were, then 3 squared plus 4 squared would have to equal 5 squared. 3 squared is 9, 4 squared is 16, they add to 25, and 25 is 5 squared. So 3, 4, and 5 can be lengths of a right triangle. The ones that you'll see in your test will probably be more complex than that, but that's the same method that you'll use. So make sure you have your calculators ready. How about this one? Runners in a long distance race start out going 8 kilometers east and then head north for the remainder of the course. The finish line is 10 kilometers from the starting line. How far did the runners travel north? So you might want to sketch this out on a piece of paper. They've gone 8 kilometers east, then they turn north, and you don't know how far. But you do know that when they end up, they are 10 meters from the starting point. So you've got the hypotenuse. You don't have one of the legs, which we'll call B. 8 will be A, and C will be 10. So 8 squared plus B squared equals 10 squared. Solve the ones you know. 64 plus b squared equals 100. And just like an algebraic equation, you'll subtract 64 from both sides. 100 minus 64 is 36. And if b squared equals 36, you know that you can take the square root of both sides and find out that b equals 6. Okay, now from the Pythagorean theorem, several other equations were developed. The distance formula, the circle formula, and several other applications of this type of relationship between the sides of right triangles. You must have the distance formula in your notes. You'll be using it quite a bit. Remember, all you do if you have 2 points is subtract the x values and square them, subtract the y values and square them, add them together and take the square root, and you'll find the distance between any 2 points. For instance, if you had the point 3, 8 and negative 1, 9, you would, under the square root sign, subtract 3 minus negative 1, and remember that subtracting negative 1 makes 3 plus 1. Then you would subtract the y terms, 8 minus 9. It doesn't matter which order you do them in, the distance will be the same. 3 plus 1 is 4, and 4 squared is 16. 8 minus 9 is -1. -1 squared is 1. And 16 plus 1 is 17. So the distance here would be the square root of 17. You might be asked to simplify your radical answer, or you could even submit it in the form of a decimal, but putting it in the form of a square root is just fine. The midpoint formula often comes in handy because you'll be looking for something that's midway between 2 points. It might be incorporated with the distance formula for a complex problem, but it's a pretty simple formula if you look at it. What you're doing is you're taking two x terms, adding them together and dividing by 2. Then you're taking two y terms and adding them together and dividing by 2. Basically, you're taking the average between the 2 points, and it automatically gives you the midpoint. So with -2,5 and 4, -9, I would add together the two x terms, -2 plus 4, divide the sum by 2, and that will be the x point. Then I'll add 5 plus -9, or just -9, over 2, and that will be my y coordinate. Well, -2 plus 4 is 2, and 2 over 2 is 1. 5 minus 9 is -4. -4 over 2 is -2. So the point that lies exactly in between these 2 points is 1, -2. And you look at it, you know, halfway between -2 and 4, yeah, 1 seems pretty reasonable. It's 3 spaces from each of those. And halfway between 5 and -9 would be -2. And if you put this on a graph, it would be even more obvious. And I do recommend that you have a piece of graph paper with you when you're taking this test, because some of these problems become more obvious if you can see them in a visual way. Quadratic functions look like parabolas or curves. They're always symmetrical, and they have a few attributes that you need to be familiar with. First of all, there's a telltale sign. If you're looking for a quadratic function, it will always have an x squared. That's what creates this shape. Remember that a squared number can never be negative, so it turns around similar to what we used with our absolute value functions. One way to write it in standard form is ax squared plus bx plus c equals 0. This gives you a lot of good information. A is the first coefficient, b is the second coefficient, and c is the constant. And we'll be getting to use these coefficients in some important formulas, such as this next one where we find the vertex. If we wanted to graph a parabola, we could use an online graphing program like Desmos.com. Maybe we don't have enough information for that. Maybe we need to formulate something ourselves. Maybe we need to answer a question that relates to how the graph looks. This little formula is very handy. -b over 2a is the x value of the vertex, or the place where the curve occurs, and key to the line of symmetry. So if you look at this example over here, you can see that the vertex down here is 2, -4. And this 2, the x value, is the one that you can find with that formula, and it's also key to this axis of symmetry or line of symmetry. This is the line x equals 2. So when you find this number, it is not only the x value of the vertex, but it's also the way you name the line of symmetry that comes in between both of the sides of the parabola. Now, what I've shown you here is not the basic graph of y equals x squared. Y equals x squared is the most basic of the parabolic functions, and it has a vertex at 0, 0. So if I had to draw it, it would be something like this. It would be symmetrical around the x-x. And you can see that a parabola doesn't have to stay there. It can shift left or right, it can shift up or down, it can even flip upside down. And some of the things that you'll be able to notice is that the telltale sign in the equation will tell you what happens to it. For instance, If y equals negative x squared, and it doesn't matter how long your equation is, if the first term, the x squared term, is negative, then it will open downward, and it's called a reflection across the x-axis. If it's the basic formula and a number is added or subtracted after the number is squared, this moves the parabola up or down. With plus 2, it moves it in the positive direction or up 2 spaces. If there is an addition or subtraction inside the parentheses before they're squared, this moves the parabola left or right. And this is a little counterintuitive because when it says minus 2, that means it's going to move to the right 2 spaces. So you might think minus 2 goes left because normally when we're graphing something on the coordinate plane, it would move to the left, but it's just the opposite, and that's because it's squared. And similarly, if it said x plus 2, it would move it to the left. Now, this example right here has been moved 2 spaces to the right, and it's been moved 4 spaces down. So if I had to write this, I would write y equals x minus 2, because it moved to the right, squared, minus 4, which moved it down. And that's why the vertex is where it is. Let's look a little bit more about why we use parabolas and why they're important. Oftentimes in a parabolic or a quadratic function, you will have solutions that could be either one solution, 2 solutions, or no solutions at all. And the way that you find those solutions are looking at the graph. It's the point or points where the graph intersects the x-axis. So you can see here in our basic graph here on the left, the only intersection with the x-axis is right at the origin at 0, 0. And that's our basic function. When the graph shifts, like this one, which was x minus 2 squared minus 4, it shifted down. Once it shifts down below the x-axis, it's going to intersect the x-axis in 2 places. So if you have a question that says, hey, compare the number of solutions or the number of x-intercepts or the number of roots between y equals x squared and another type of the formula, you should be able to tell how many roots or how many times it crosses the x-axis. Remember, it can never be more than 2. It could be 1. But let's say that our graph moved up and the vertex was up here above the x-axis and the graph existed someplace up here, it would have no solutions whatsoever or no real solutions. Now, similar to our work with quadratics and regular functions are quadratic inequalities. There's absolutely no difference in the way that you solve these, just like when we were working with inequalities and equations, but the solution will be a zone on the plane, not a single number, not a single line, not a single curve. And it will either be shaded above the curve or below the curve, depending on the direction of the inequality sign. If the inequality sign comes after y and y is isolated and it's greater, then the shading will be on top or inside the curve. If, on the other hand, it were less than, then it would be shaded outside the curve. Now this one, you can see x plus 2 is inside the parentheses before the squaring occurs, which means that it was moved 2 spaces to the left. You'll also see that the line was drawn with a dotted line. That's because the solutions on the line of the curve are not actually part of the solution set, and that's indicated by this inequality sign. It doesn't have the equal portion under it that would be required for this to be a solid line. There are many ways to solve quadratic equations. You can graph it and you can detect where it goes through the x-axis. You can factor it and use the zero property. You can use the square root method, or you can complete the square. So let's just look briefly at some examples what you could do. Now we talked about factoring quite a while ago, and this one doesn't look quite right for factoring. We'd have to fix it first by pulling all of the terms to the left, and if I did so, I would be subtracting 15 from both sides, and I would end up with an equation that equals 0. Then I would draw my two sets of parentheses. I'm going to look for two factors of 2x squared. I'm going to choose 2x and x. Since the operation sign before the last number is negative, I know I'll have a plus sign and a minus sign, and I'm looking for two factors of 15 that will combine to make 1 in the center. So some options are 5 and 3 or 15 and 1. 15 and 1 is going to make either a very large or a very small number depending on which place where I put it before or after the minus sign. So I think I'll head for my 5 and 3. And yes, there's a little bit of guess and check in here. If I put my 5 here, for instance, and my 3 here, I know that my middle term will be determined by combining my outside terms when I FOIL and my inside terms. And here I've got 2 times 3 equaling 6, 5 times x equaling 5x. Combining them would give me 1 if I subtract the 5x. So I'm going to put my minus sign in front of the 5 so that 5x gets subtracted from 6x. And these two factors are the ones that would work for this quadratic equation. So let me just get rid of that. So what can we do with this and how do we find the solutions? Well, if this whole equation equals 0, the only way to get 0 is to multiply something by 0 or divide something by 0. Well, you can't divide by 0. So either 2x minus 5 equals 0 or x plus 3 equals 0. Well, if 2x minus 5 equals 0, then 2x has to equal 5 and x would equal 5 divided by 2. If x plus 3 equals 0, x plus 3 equals 0, then subtracting 3 from each side gives me x equals negative 3. And so this 0 property allows you to use the fact that the original equation was equal to 0, factor it into two factors, one of which or both have to equal 0. If the x equals 0, if the x equals a value when the quantity equals 0, then these are the points where that parabola are going to cross the x-axis, and these are considered the solutions to the quadratic. Now, since there's always an x squared, there's always an option if you have a certain type of equation to solve it by the square root method. So for instance, in this one, 6x squared minus 24 equals 0. If I add 24 to both sides, then I get 6x squared equals 24. If I divide both sides by 6, I end up with x squared equals 4. Now, at this point, your goal is to get the x squared all by itself. And if you can take one more step, and that is to take the square root of both sides and realize that x equals plus or minus 2. Why plus or minus 2? Because positive 2 squared is 4 and negative 2 squared is 4 also. So there are two solutions, either x equals plus 2 or minus 2. Okay, well, what about this one? Why did I put this in this category? Well, because the x minus 3, even though it's in parentheses, it is being squared. So I could still take the square root of both sides. If I did so, the square root of x minus 3 squared would simply undo the squaring and it would become x minus 3. But remember how we use the plus or minus 2? That would either equal the square root of 5 or the minus square root of 5. So that's going to be plus or minus square root of 5. To solve for x, I would still have to add 3 to both sides. So x equals plus or minus square root 5 plus 3. Not as pretty of a solution, but still two very good solutions that would work for this equation. Now, completing this square, some people love it, some people hate it. Sometimes it's difficult to figure out, but once you've done it a few times, it's not so bad. If you remember in a perfect square trinomial, well, let's just take this one for instance. We had here x minus 3 squared. If I have x minus 3 squared, I can expand it to make x minus 3 times x minus 3. If I use FOIL to multiply these, I get x squared for my first terms, negative 3x for my middle term, for my second term, negative 3x for my inside terms, and positive 9 for my last terms. And those two middle terms will combine to make minus 6x. So the quadratic that this came from was x squared minus 6x plus 9. Now, you'll notice that it makes a certain pattern. This is always a perfect square in the first position. This last one is always a perfect square because you've multiplied whatever numbers you have by each other. And if you notice this middle term, it has a pattern as well. It's 2 times the square root of the first and third terms. So here the square root of x squared was x, the square root of 9 was 3. So that would be 3x, and double that would be 6x. So let's take a look at this x squared minus x and figure out what would we have to add to the end of it to make a perfect square trinomial. Well, we know that it's going to factor out to be x, so x is the square root of that. And we know that this middle term has to be twice as much as the last term's square root. Well, right now it's 1. So half of that would be 1/2. So this term over here in the third place would have to be 1/2 squared. In order for 1/2 to be its square root, and that when we combine these two and double it, it becomes 1x, or in this case, negative 1x. So what is 1/2 squared? It's 1 squared over 2 squared, which is 1/4. So if I wrote this out, x squared minus x, and I added 1/4 to it, then I know that this is a perfect square trinomial, and it would be called completing the square. This is a very important method in solving some more complex problems, but in this case, it would allow you to factor this and find some solutions to this quadratic. One great invention is the quadratic formula. This can be used on any quadratics. The treatment that I showed you before might be the best or easiest choice for any of the particular ones that you come across, and you should be able to do all of the methods. But remember, they all work in this method, and sometimes this is just downright the easiest one. So remember that formula I gave you with ax squared plus bx plus c. Those numbers come into play in this equation, and I'll show you how it works with this equation. First, identify a, b, and c. There's no coefficient showing up in front of x squared, so a equals 1. The second one is 5, so b equals 5. The third one is negative 5, so c equals negative 5. Here's how the equation would work. X equals negative b. Well, my b was positive 5. So negative 5 plus or minus, you'll notice that many of your solutions are going to be plus or minus because of the square roots involved. The square root of b squared, well, my b was 5. 5 squared is 25. Minus 4 times a times c. Well, a is 1, c is negative 5. Together they make negative 5. And 4 times negative 5 is negative 20. So 25 minus negative 20 would be the same as 25 plus 20. And that is going to be a fraction over 2a. And my a was 1. 2 times 1 is 2. So to simplify this, let's see what we can do. We've got minus 5 plus or minus the square root of 45 over 2. Well, I know I can simplify 45 because it happens to be 9 times 5. So if I consider that to be the square root of 9 times 5, it's also the square root of 9 times the square root of 5. And the square root of 9 is 3. So instead of square root 9, I can use square root 3 and rewrite this as negative 5 plus or minus 3 times the square root of 5 over 2. And this is actually a solution that you're going to find on your test. If you didn't follow that, kind of stop the tape, go back, take a look at it again. Make sure that you try a couple of examples before you get to the test. Now the circle formula is very, very similar to the distance formula, and it is a quadratic formula, but it doesn't make a curve, it makes a circle. What a circle is just a collection of all of the points that are equally distant from the center. Now, one of the crazy things that happens is if the center of your circle is 0, 0, then the equation of the circle is always exactly the same. It's x squared plus y squared equals r squared. Why does that work? Because let's imagine that you have a right triangle inside this little circle, and one of the sides would be x, one of the sides would be y, and you would create a right triangle here. This would be your radius, obviously, and then this would be your x, this would be your y, and so it's really the Pythagorean theorem just all over again. But because you want the collection of all of them, you make a general formula in the form of x squared plus y squared equals r squared. And in this particular situation, we know the radius is 5. So the equation for this would be x squared plus y squared equals 25, which is 5 squared. Now, in your course, you're going to be introduced to some exponential functions as well, and you're also going to be introduced to some systems of equations. Remember when we did systems of equations when we're talking about linear equations only, the solution was where the two functions intersected. So if it was two lines, it would just be one point, or they might be parallel and there'd be no solution, or they might be the same line and have an infinite solution. Well, here we're going to explore that a little bit. We're going to use the same techniques, but one of our functions might be exponential, like this one here. One might be linear, one might be a parabola. So you should be able to use these same methods with all types of functions. If you were given a problem just like we used to do when we were only talking about linear functions, and one of your functions is already solved for one of the variables, that's a heads up that you might be able to use substitution. So let's say that you were given these two, y equals negative x plus 7 and y equals negative 0.5 times x minus 3 squared plus 8, and you want to do this by substitution. Well, they both equal y, so I'm going to substitute negative x plus 7 for the y in the first one, and then solve, because now I only have one variable. And I can easily get my x solution by solving, and then I can go back and get my y solution. So this looks pretty complex, but we've already discovered some things that we can do. So for instance, I want to get rid of this 8 first. Remember, I'm trying to either get to something squared or expand something and then simplify it. So if I subtract 8 from both sides, I'll subtract the 8 from the 7. So then I have negative x minus 1 equals negative 0.5 times x minus 3 squared. Now, at this point, I could expand my x minus 3. I could divide both sides by negative 0.1. But what I think I would do is expand this x minus 3. And remember, this is the same one that we did before. So this was the one that was x squared minus 6 squared plus 9. And this is still being multiplied by 0.5. Now, if I want to multiply across, I'll just use the distributive property. I get 0.5 times x squared. 0.5 times negative 6 is negative 3x. And 0.5 times 9 is 4.5. Now right now I'm working with some decimals, and if that looks messy to you, remember that you can always multiply the whole thing by 10, get rid of those decimals. But right now I just want to simplify, so minus x minus 1. I can add x to both sides. I'm just going to pull this down here because this one isn't going to require any work. If I add x to both sides, I end up with negative 1 equals 0.5 x squared. And I've got one more x here, so now that's going to change to minus 2x, because negative 3 plus 1 is negative 2, plus 4.5. I just got one more thing remaining over there, and that's that negative 1. So if I add 1 to both sides, I end up with 0. That's 0.5 x squared minus 2x, and I'm adding 1, so now I'm going to have 5.5 instead of 4.5. Now, this is almost in general form. I'm going to multiply this whole thing by 2, make it a little bit prettier. There's nothing wrong with this solution at this point, but if we wanted to use this in, say, one of our equations or something to solve for a solution, it would be easier. 0 equals x squared minus 4x plus 11. Okay, now I can see right away that I wouldn't want to factor this, but perhaps I'd like to take this into the quadratic equation to solve it. If I did that, I'll just switch over here. I'd have minus b. Remember, b is negative 4, so that would be 4 plus or minus the square root of b squared. B is negative 4. Negative 4 squared is 16. Minus 4 times 1, which is a, and 11. So 4 times 11 would be 44. Over 2 times a, which would be 2. Now, if you'll notice something here, we've got 16 minus 44 in our square root symbol, and that's going to create a negative number. A negative number in a square root is undefined, or imaginary actually, so this is going to have no solution. So even though there are a lot of things that we can do to simplify it, sometimes it does come out with no solution. If we went and graphed this, it would be a parabola, but it would not hit the x-axis at all. Okay, now even though I've messed up my screen a little bit, let's look at this other one. Solve the system 7x plus 3y equals negative 3 and y equals negative 2 to the x by graphing. Well, we've got this handy tool, Desmos.com. I'd like you to have it open in a tab when you get to your test. And you can see that this first one is a linear equation. We could simplify this into slope-intercept form, but we can see that it's passing through the y-axis right at negative 1, and that it's intersecting the exponential graph at 2 points. Now, a line and an exponential graph don't have to intersect, just the same as a parabola in a linear function. Graphing is an excellent way to find out whether they do have solutions. Sometimes it's difficult to find out what exactly those solutions are, but in Desmos, if you hover your mouse over the points where they appear to intersect, it will tell you the location. So a very handy tool. Now, why do we use these quadratic equations? Well, there are some very practical reasons. Here, the length of a rectangle is 3 more than twice the width. The area of the rectangle is 1/19. What are the dimensions of the rectangle? If you use x for the width of the rectangle, what would be the equation to solve the problem? So in this one, let's take a look at it. We've got length, let's talk about that as L, or let's call it y because they've already called the width x. Okay, we're going to call that y. There's my verb, 3 more than is 3 plus, twice the width. Twice the width is represented as 2x. The area of the rectangle is 119 square inches. If x is the width, what would solve the problem? So we want to know the dimensions. We want to solve for both x and y, and we know that the area is 119. So the only thing we can really do is to multiply x by y. And instead of just the letter y, I'm going to use its equivalent and substitute this 3 plus 2x for y. So, 3 plus 2x. And you'll see why this is a quadratic equation when I multiply. X times 3 is 3x. X times 2x is 2x squared. And I know that that's going to equal 119. Well, if I put this into a nice quadratic form, I would subtract 119 from both sides. So minus 119. Now it's going to equal 0. I've got 3x plus 2x squared, and those need to be in the other order for me to determine my a, b, c. So this is 2x squared plus 3x minus 119. And if I took this directly to the quadratic formula, I would do minus b, which is minus 3 here, plus or minus the square root of b squared, and 3 squared is 9, minus 4 times 2. I'm going to have to do a little math here on the side. I've got AC is 119 times 2, so that's going to be 238, and if I multiply that by 4, then I get 952. So that's going to be, and it's going to be plus, let's see, hang on. 4AC, this was negative 19, so this is negative 238, so this is negative 952, so it's going to be plus 952, and that is going to be over 2a, which 2 times 2 is 4. 9 plus 952 is 961, so negative 3 plus or minus square root of 961 over 4. Now, unfortunately, I don't have my calculator available while I have my screen open, but if you simplified this, you could get 2 actual values for x. And remember, this is x equals. So once you find the 2 values for x, you can use them in the, substitute them into this equation to find the other dimension of the rectangle. Now, you're not actually going to be required to solve this equation. You're going to come up with this equation that would be one that you could use to solve it. Okay, so I don't want to scare you off that you're going to have to go and graph this or use this equation or whatever. You're just asked to find the equation that you would use to solve it. There are some, however, that you will want to be able to solve. This one is not too bad. A ball is launched into the sky at 272 feet per second from the roof of a skyscraper 1,344 feet tall. The equation for the ball's height at time t seconds is h equals negative 16t squared plus 272t plus 1344. When will the ball strike the ground? So this is one that just requires some thinking. First of all, you're at the top of a very tall building, and you can imagine it as it were being on a coordinate plane, say, and you are at level 1344. You launch the ball into the air and you create a trajectory that looks a lot like a parabola. Now this is upside down, which makes sense because we've got a little negative 16t squared here going on. And we know that the vertex, or the maximum for the rocket that's thrown into the, or the ball that's launched into the sky, is going to be right there, but that's not what they ask us for. They want to know, when does it hit the ground? So you need to ask yourself, well, what time is it when the height is 0? So basically you are going to replace height with 0 and solve for this equation. Minus 16t squared plus 272 t plus 1344. Okay, now this one can be simplified a little bit. You can tell that, let's see, I think each of these is divisible by 4, maybe even by 16. So you could bring this down and simplify it quite a bit, because once it's equal to 16, you can divide all of the terms by the same number without changing the fact that it's equal to 0. Then you could see if if it was easy to factor, if it's easier to use the quadratic formula, or what method would be the easiest way to solve for t at this time. But remember, you're solving for t. The tricky part of this question is, wait, where's the number for h? And you need to remember that h will be 0 when the ball strikes the ground. Here's another one. Tommy and Zach are starting out at the same position. Tommy runs north at 5 miles per hour, and Zach starts to run east at 2 hours later at the rate of 8 miles per hour. How long until Tommy and Zach are 16 miles apart? Okay, so let's just kind of map this out. We're starting at the same position right here. Tommy runs north at 5 miles per hour, and Zach starts to run east at 2 hours later at the rate of 8 miles per hour. How long until Tommy and Zach are 16 miles apart? Well, do you remember that distance equals rate times time, right? So we've got two distances going on, and we've got some time figures, and we've got some rates here. So the distance here is going to be 5 miles per hour, which is the rate, times t. Okay, that's going to equal this distance right here. So this is 5t. Now, when Zach starts running east, he's going 2 hours later, and his distance is going to be 8 times, and it's not going to be the same t. It's actually going to be 2 hours less than what Tommy was running. So we're going to use t minus 2 here. Okay? And we want to get to some place where they are 16 miles apart. Well, the distance between them is actually going to be a hypotenuse of a right triangle, because one went north and one went east. So let's see if we can figure this out. And if we know that the hypotenuse is 16, we're going to figure out what these other sides are. Let's kind of expand our 8 times t plus 2 to be 8t minus 16 and use our Pythagorean theorem. We know that 5t squared plus 8t minus 16 squared is going to equal 16 squared. Okay, so there's a little bit of math here to do, but you're going to simplify this out by doing the squaring, 25t squared, and that's where you're going to get your quadratic. And then if you had to multiply this out, you're going to FOIL. So 8t times 8t is 64t squared, and 16 times 16, I believe, is 256. And the middle term is going to be double the square roots, and 8 times 16 is 124, and double that would be 248. And that's going to be minus, okay, and that all equals 16 squared, which I believe is 256. Okay, so if we combine any like terms, we've got our 64 minus 248. So that is going to be minus 184t. And at this point, we want to set this equal to 0 so that we can use one of our methods for solving. So we're going to subtract 256 from each side, and you can see that they will both cancel out, leaving us with 25 equals, or 25t squared minus 184 equals t equals 0. Now here we could use the one method where we subtract 1 from each side. 25t squared equals 184t. We could divide both sides by t and get 25t equals 184. And then we could divide both sides by 25, and that's going to equal 184 over 25. So it's not going to come out even, but you could divide that out to find out the time that it would take. Now that time is going to be how long it takes them until they're 16 miles apart. And you're going to round to the nearest tenth if necessary, because obviously this isn't going to come out even. So that is the method that you would use. It takes a little bit of time, but it's all skills that you already know how to do. Okay, I talked a little bit briefly about exponential functions. They look quite different than quadratic expressions and equations. They have an L-shaped curve, but they change around in a similar way to how we changed our parabolas. So here's kind of a basic function up here. This I've graphed y equals 4 to the x power, and you know that it's an exponential function, number one, if it has an L-shaped graph, and number two, if it has the x as the exponent. It's not part of it. There's no exponent of 2 like we saw before. Now the x is the exponent. Now let's say that you changed it out and you had y equals negative 4x. Well, that would be reflected across the x-axis, and it would turn out to be like this blue one. It flips it upside down, reflects across the x-axis. What about if you have y equals 4 to the negative x? The exponent becomes negative. That flips over the y-axis, so it's going to be facing the other direction, like this green one. Okay? What if we add 1 to the exponent, or subtract 1 from the exponent? That shifts it to the right 1 unit. That's this blue one. But what if something is added after the exponential term? That's going to shift it up in the same way that happened with our parabolas. So those are some similar patterns that you can discover. And if you want to go into Desmos and fool around and look at how things change, put in the basic formula and try changing a few things and see how it shifts. Now, one part of your test is where you're combining functions. So you might be given a couple of different functions, and you might want to know, well, what happens if one happens first and then the other one happens? So here's an example. One of your function is s of x equals 3x minus 6, a linear function, and t of x equals 6 minus 3x, another linear function. Find the simplified form for v of w equals st of x, and w of x equal, oh, this should be an x. Sorry. And w of x equals t over s of x. Well, it looks super, super complex, but all you're really doing is putting function s over function t. So I've done 3x minus 6, which is s, over 6 minus 3x. And you're asked to find the domain. Okay, so we could figure this out. We could actually find out, well, let's say that I multiplied the top and the bottom by -1, which is allowed. Put a -1 up here times, well, let's say that I rewrite the bottom. This is going to be much easier. 3x minus 6 will leave alone on top, and I'm going to rewrite the bottom. If I multiply the bottom by -1, I would have to multiply the other factor by -1. That would be -6 plus 3x. And if I change the order, that would be 3x minus 6, same as what I have on top. So now I can see that the 3x minus 6 cancels out, and I am left with just 1 over -1, which is -1. And I could do the exact same thing down here. This is 6 minus 3x. And if I change the bottom to be -1 times 3x minus 6, which is positive 6 minus 3x, then they would cancel out as well, and I would be left with -1. So you say, well, what's the difference between them if they both equal -1? Well, the difference is the domain. Remember, the domain is all the values of x that will work for a function. In this one, the only restriction to the domain is going to be that we can't have 0 in the denominator of a fraction. So what would the value of x be if 6 minus 3x equals 0? Well, adding 3x to both sides gives me 6 equals 3x, and dividing both sides by 3 means that x would equal 2. So this is all real numbers, but x is not equal to 2. So what would that look like? It would look like x equals -1, a straight line, but there would be a hole in the line where x equals 2. What about this other one? If 3x minus 6 equals, 3x minus 6 equaled 0, what would be the value of x? Adding 6 to both sides gives me 3x equals 6, and dividing by 3 gives me x equals 2. Same thing. So x equals 2. So 6 minus 6, 6 minus 6. They both have the same domain. All real numbers except x is not equal to 2. All right. Comparing functions. You have a problem in your test that is exactly this question. It says, use technology to approximate the solutions to the system of equations to the nearest tenth of a unit. I don't expect you to be able to work out these complicated problems, but you should be able to graph them in Desmos. And you can see that the solution or solutions is going to be the place where all of the functions intersect, well, where any of the functions intersect. So this blue line is g of x equals the absolute value of x. You might recognize that. And the other function is these 3 purple ones. It's a 3-part function, and that comes into place because there are some areas of the function that are undefined. In negative x squared plus 8 being in the denominator, there are a couple of places where it can't equal 0. So these pink ones are all the same function, and you're just looking for the points where they intersect. And in this case, you've got negative 3.3, 3.3, and 3, 3. So they want you to approximate those solutions. You're going to look at the graph. You might not be able to find exactly what those solutions are, but you'll be able to get them, especially if this is a multiple choice question. But don't hesitate to use Desmos.com for your graphing. Okay. So let me tell you, this test has 49 questions. Allow yourself a good amount of time. You can see there's quite a bit of calculation. Have your Desmos.com open in another tab. If there was something in this review that you noticed that was really going to trip you up and you'd like to see again, just let me know. I'd be glad to review it with you before you start. All right, good luck on the test.